Okay, so we're going to move on to the next topic, which is the product and quotients of functions today. It's going to be very similar to the last lesson where we did sum and difference of functions, except of course we're just doing multiplying and dividing instead. So again, we're continuing on with this. We're going to start with a quick review of sum and difference of functions. It's actually going to be a diploma question, I'll just tell you right now. I know we don't have a diploma exam this year, but I think it's still a really good question and worth going over. Then we'll look at products of functions, then quotients of functions, and then the effect, or the effect, I think it should be, these operations have on domain and range, right? So anyway, let's get going here. Start with that diploma question. So this diploma question has a correct answer rate or whatever of 61.2%. It's showing the graphs of f of x and g of x. F of x is on the right or on the left, and g of x is on the right. It's asking for the range of the graph of h of x equals f minus g of x, and it's one of those options down there. If you want, please pause the video here, give this one a try. You'll really want to look at both of these graphs. That's my only hint I'll give you, and I'll go over it in just a second. All right, so actually having this in front of me is going to give me a huge advantage over someone who tries it without actually jotting anything down. What I would do in a question like this is I would actually physically draw the graph of h of x, which is f minus g of x. So f minus g of x means we just take the y values on f and we subtract the y values at the same location of g. And it's kind of unfortunate that these are on two different graphs, but it's not too hard to stitch it all together. Notice at -2, when x is -2, f is -4, and then we want to minus +2, right? So -4 minus 2 is -6. So that point can go there. The next point I'm going to use is how about when x is equal to 0. When x is equal to 0 on f, y is 2, but on g, it is -1. 2 minus -1 is 3. So in other words, it'll be 3. And then this next one, on f, when x is 2, y is 8, and when x is 2 on g, y is -4. So 8 minus -4, that would take you way up here to 12, right? So 12, we're completely off the charts, but I'm going to just still jot it in anyway. And if we were to graph h, I'm not going to be very exact here, just sort of squiggle a line in, it'll look like that. So the range, we can see the lowest value is going to be -6, and the highest value for a range of h is going to be 12. And what do you know? That's going to be c, because y is going to be between -6 and +12, and that's inclusive, right? Not a bad question once you draw it out. It's actually kind of a little strange that more people didn't get it right, but I think the main reason is it was on two different graphs, and maybe some people didn't think of drawing it. If you didn't draw it, it would be a hard question, I put it that way. Anyway, moving on. Products of functions. Given that f of x is x and g of x is -2x plus 2, determine a function for h of x, where h of x is f of x times g of x. Now, they usually just put like a little closed dot right there to represent multiplying in this, because you wouldn't want to put an x. It would kind of like confuse you with the other x's here. But again, let's just determine a function for h of x. This is just like before. Like, it's kind of actually silly even doing this. H of x is going to be f of x. F of x is just x times by g of x. G of x is -2x plus 2. Now, of course, it's important to put the brackets there because we have to see that this x is going to double dip through the brackets here. So this will be h of x equals x times -2x is -2x squared, and then x times +2, which is plus 2x. That's literally all there is to it, right? No big surprise. That's all there is to that one. Oops, I think I went. There we go. Now we're good. Now, in terms of a graph, though, we're going to notice something that you probably could immediately predict right now. I'll try to do this as quick as possible. Sketch the graph of each of these, basically. So f of x is x. That's literally just, you know, f of x is x. Okay, you know what? I'll do my dots. I'm not gonna try to do this freehand. Do the dots here. F of x is x. So in other words, y is equal to x. You know, y-intercept of 0 and a slope of 1, if you want to put it that way. Put all the dots in here, and I know how annoying it is, but the dots are super, super vital for this. Try connecting this with a line as best I can. You guys know this is my favorite thing in the world. Here we go. Kind of getting off beat there. Not too bad though. Good. All right. So we're good there. Now I'll switch pen color. I'll do blue for g of x. That kind of scribbled it out. There we go. G of x. -2x plus 2. So 2 is our y-intercept, and our slope is -2. So we're going to go down 2 over 1, down 2 over 1, down 2 over 1, and so on. There we go, and then just do it in reverse. There we go. Now connect them with a line. Awesome. It's coming together now. Awesome. Good. All right, now sketch the graph of h of x, which is the product of those two. I'll do it in green. Remember, h of x, as we determined before, was negative 2x squared plus 2x. You've got some choices on this one. You could do what we did on that lesson before, where we basically just find the vertex and then do the 149 rule. I'm very comfortable with that, so that's what I think I'm going to do. Just a reminder, on a quadratic, and this is a quadratic because it's an x squared function, the vertex is going to be x equals negative b over 2a. So in this case, we have x equals negative b is negative 2 over 2 times a. 2 times a is 2 times negative 2, that's negative 4. So negative 2 divided by negative 4 is 0.5. Okay, not a big deal. We'll have a vertex at 0.5. Now, if you want to find what the y value is for that, you just plug in 0.5 into this. I am going to use a calculator on that one. Negative 2 times 0.5 squared plus 2 times 0.5. And that's going to give me actually something that isn't too terribly bad. It's actually going to give me 0.5. That's kind of interesting. So at positive 0.5 and positive 0.5, that's where we're going. Oops, not there. It's got to be right here. What on earth am I doing? That's where we're going to have a vertex right there. And just judging by how this picture looks, it almost looks like that's at the total intersection point between those, but that's kind of interesting. Then you can go with your 149 rule, go over 1 and then up 1 times a. Well, a is negative 2 in this case, so we're actually going to have to go down. So we're going to go over 1 and then down 2. So 1, 2, there you go. Then we'll go over 2, and then we're going to go down 4 times a. So 4 times negative 2 is negative 8. So we're going to go down 1, 2, 3, 4, 5, 6, 7, 8. And it doesn't look like the 9 part's going to work. So I'm not going to worry about that. I'll just make it symmetrical on both sides. There we go. And then draw it as such. Now, another way we could have done this, because again, on this case, more so than ever, oh my goodness, that was bad, hold on. This case, more so than ever, that wasn't much better, but you know what, I'm just gonna deal with it. This case, more than ever, it would have just been easier to plot your points just by looking at the coordinates on your original graph. Just like before, if you wanted to graph this, you could also just select certain coordinates and multiply them together. For instance, notice I'm just gonna say at x is equal to 2, on the red graph, we have y is 2, and on the blue graph, we have y is negative 2. Well, 2 times negative 2 is negative 4, so it's really like we're crossing right there. If you chose another point, like let's say, I guess really we could say 0 and 2, that should be crossing right there at that 0. I just didn't draw it very well. And then same with this one here, where blue is at 0 and red is at 1, it should be crossing directly right there as well. So how could you have used the graphs of f of x and g of x to make h of x? Just multiply their y values. That's about all there is to it on this one. Okay, I'm not going to spend any much more time on that than I have to. All right, so next one, we're going to do a quotient of function. It's exactly how you think it would be, except there's going to be one little thing we're going to watch out for, as you can see on the bottom here. Consider that f of x equals x squared plus x minus 6 and g of x equals 2x plus 6. Create a simplified equation for h of x equals f over g of x. That literally just means take f of x, and divide it by g of x. Now, hopefully this is kind of ringing a little bell, like a little bell in the back of your mind right now. Like there should be like something just ringing right now. Because this f of x over g of x, this is basically a rational expression. That was what our entire last chapter was on. It was on rational expressions. And the exact same relationships that exist in rational expressions are going to apply here. A quotient of two functions is by definition a rational expression. So what we're really going to end up with here is h of x equals f of x, which is x squared plus x minus 6, divided by g of x, which is 2x plus 6. But hopefully what you remember from the rational expressions unit is we can find a lot of really interesting pieces of information from this just by factoring it. Now, the numerator can factor by the sum product rule, two numbers with a sum of 1 and a product of negative 6. That would be 3 and negative 2. So this is x plus 3 times x minus 2. And then the denominator, the only way we can factor this is just to take out a common factor. And a common factor would be 2 there. So it would be 2 times x plus 3. Now, what I want you to notice is x plus 3 shows up on both the top and the bottom. So technically, those can get knocked out. Now, hopefully what you remember is, though, when we knock out something like that on the top and the bottom, that becomes a point of discontinuity. So we can't forget about that, but I will polish this off by saying h of x equals x minus 2 divided by 2, just the leftovers there. But it is important that we note that we have an NPV, a non-permissible value of x cannot equal -3. So is there anything you need to watch out for here? Yes, it's your NPVs. And you might also want to identify the type of NPV that they are, right? So in other words, maybe we should also identify in this NPV that it's a point of discontinuity. If it was a vertical asymptote, that would be another story altogether. You could say it's an NPV of that, it's a vertical asymptote. But in this case, because it was on the top and the bottom, we know it's a point of discontinuity. So in other words, if we were to graph this in our calculator, it wouldn't look like it shows up in a calculator, but if we were actually supposed to graph it at x is -3, we'd have to put a circle, right? An open circle to denote that it's a point of discontinuity. All right, next up, sketch the graph. Oh, here it is. See, there we are. We actually are doing this. So sketch the graph of that, and then sketch the graph of h of x. So let's take care of this one step at a time. Let's do our normal functions here first. I'm going to start with this guy. This is honestly going to be probably the beefiest piece of it all. X squared plus x minus 6, probably a good idea to find your vertex. So your vertex is going to be x equals -b, so -1, divided by 2 times a, so times 2 times 1, which is 2. So in other words, -1/2, -0.5. If you plug that in there, I'm just going to do it real quick. -0.5 squared. Oh, hold on, just put that in wrong. Got to square the outside of the brackets, not the inside of the brackets. -0.5 squared plus -0.5 plus, or sorry, minus 6, not doing too well today. That's going to give me y equals -6.25. So I'm going to plot that coordinate, -1/2 and -6.25. That looks like it's about right here. It's not perfect, but that's just how it goes. And then we can use our 149 rule. 149 rule says go over 1 and then up 1 times a. Well, a is just 1 here, so we'll go over 1 and then up 1. So about there, and I guess -5.25. And then you go over 2 and then up 4. So that'll leave us about right here. And then you go over 3 and up 9. So that'll be about right here. You probably can do the 149/16 rule too. You know what, I will do that because from just under -6 to up to just under +10, that would be where that would end up. So I will put that one there as well. And then I'll just make it symmetrical on both sides. There we go. There we go. And there we go. If you're anything like me, it's really bugging you probably that the dots we're putting in aren't actually at very specific marked points, but that's just the way it goes. And then connect all this and connect all this. There we go, good. All right, now g of x, this one will be a lot easier. G of x, I'll do it in blue, it's 2x plus 6, so +6 is our intercept there, and of course our slope is 2, so up 2 over 1, up 2 over 1, and then just do it in reverse. There we go, down here, down here, down here, down here, and down here. And connect it with a line. There we go, I'm just gonna leave that little blip right there, that's fine. That's fine. All right, now the real tough one. F over g of x. I'm just going to bounce back real quick. Yeah, it was x minus 2 over 2. So h of x equals x minus 2 over 2. But with an NPV of x cannot equal -3. And the type of NPV that is, it's a pod, right? If you want my honest opinion here, this might be a bit of a tricky one to graph. But probably an easier way of doing it is to take this fraction to split it into 2 pieces. X minus 2 over 2 is the same thing as saying x over 2 minus 2 over 2, right? So this really can just become 1/2 x. Let me just put it like that, 1/2 x, it's like x over 2, right? Minus 2 over 2, 2 over 2 is just -1, right? When it's like this now, you can see it's the linear equation. Okay, so it's going to have a slope of 1/2, but it's going to have a y-intercept of -1. So with -1 being our y-intercept, we're going to be looking at it right there. And then we have a slope of 1/2. Really, it's probably easier to think of the slope as a rise over run. So you can rise 1 and run 2. rise 1 and run 2, rise 1 and run 2, and so on, and then just go in reverse and reverse. Now, one thing we got to note though is that NPV we have, and we know that that's a point of discontinuity, even more so obvious that it's not going to be a vertical asymptote because this looks like it's just going to be a straight line. But at -3, when x is -3, we're going to have that point of discontinuity. And that looks like it's going to occur right here. So I'm going to put an open circle right here because that's where x is -3. And that's just where that's going to show up. So anyway, we're going to connect all these lines, leave that as an open circle right there. And there we go. Now we've cleared it. Now there's just one really big important thing I want to discuss about this before we move on to that other question, is notice our NPV lines up right here. Notice that both of our graphs, both the red graph for f of x and the blue graph for g of x, they were both having an x-intercept right there. So they were both zeroed out at that point. So kind of like what we had mentioned before in rational expressions, what we're getting with this point of discontinuity is a point where it's 0 divided by 0, right? There was a 0 for our red function and a 0 for our blue function. So that's going to give us a big problem right here, a point of discontinuity. But it doesn't affect the whole slope of our graph because both of these approach 0 at the same time, right? So that's why we just have an open little gap right there. You have to include that. You do need to make sure that that's there, otherwise it is not correct. Now, what are the domains and ranges of the three functions? Do we notice anything? Well, let's have a quick look. We'll set it up just like what we did last day. Domain, range. We'll start with f of x, so the red function. The domain of our red function is x is an element of all real numbers, right? Not a big surprise. As for our range, y needs to be greater than or equal to -6.25. That was our lowest minimum point. It was our vertex. Also not a huge surprise. Now g of x, that's our blue function. Again, we have x is an element of our real numbers, and y is also an element of the real numbers because it could go anywhere, basically. Now h of x, this is where it's going to get really curious. H of x has a domain also of x is an element of all real numbers, except x cannot equal -3. That is pretty peculiar, but there's a reason for it. We'll get to it. Now, in terms of our range, also our y can also be an element of all real numbers. However, our y just can't equal whatever it is right here. And to determine what that is right there, you just have to plug in -3 into this equation right here. So 1/2 times -3 is -1.5, and then -1. That means y cannot equal -2.5, which looks exactly like that's where that lines up. Now, do we notice anything? Well, honestly, there's not really too much to notice on this one. It's kind of strange. As it was before, your range isn't going to be nearly as predictable as your domain could have been. Now, your domain is also not super predictable here, but the thing with the domain is when you're taking a quotient of a function, your domain just cannot be whatever makes your denominator equal 0. So in other words, in terms of, just find a place to write this, in terms of h of x being f of x divided by g of x, your domain is just g of x cannot equal 0. Okay, but you actually have to find what that point is. Anyway, I'm rambling on. Now, here's another question. I guess this one's a little different because we're putting the bigger function on the bottom in this case. You know, I guess we can do this one. Again, if you're like, all right, he's beating us to death, because I honestly think this is kind of beating it to death. If you think I'm beating this to death, you can honestly just like skip forward a bit in the video, but I'll do it anyway, whatever. I'll suffer through it. I think we've just kind of nailed this too much here. You know what, before I actually do that function, I'll sketch the original graph. Okay, so x plus 2, that's an easy one to do. Start at 2, slope is 1. Just fill it in like so. Not a big deal. Again, those points are important. Maybe what I'll do just for fun on this one is I'll plot my points, but then I'll just like deal with the resultant graph just by dealing with these points here. You'll see what I mean, unless I change my mind in the next 2 minutes. Yeah, there we go. Good. Now I'll switch to blue, do the other one. X squared plus 9x plus 14. I can tell you right now this one is really not going to be fun because our vertex is going to be, I guess, -9/2, so -4.5. All right, so -4.5, we're over here. Then to find the y of our vertex, you just got to plug that in. Give me a second here. -4.5, I'm going to square that number. Then I'm going to plus 9 times -4.5. And then I'm going to add 14. That gives me negative 6.25. So negative 4.5, negative 6.25. That puts it at about right there. 149 rule, we can just kind of like expand it like we did before. 4, hold on. 1, 2, 3, 4. And then 9. It's going to be, I guess it's going to be just underneath 3. So there we go. Make it symmetrical on both sides. It's pretty bad when even I'm running out of steam on this one. I hope we all get this. I hope we all know how this process works, but if we don't, that is fine. That's what I'm here for. Here we go. Here we go. And here we go. Good. Now, if we are going to represent this final function, of course, we can just say that h of x is therefore equal to x plus 2 over x squared plus 9x plus 14. But it's nice to simplify it down if possible. So we can say that this is x plus 2 over x plus 7 times x plus 2. And what do you know? We're going to have a point of discontinuity on this one too, because x plus 2 is going to cross off on the top and the bottom. So now we have 1 over x plus 7. 1 over x plus 7 is going to be a much different shaped function than what we're used to, because there still is going to be a vertical asymptote, because there still is a non-permissible value in there. So again, maybe I should list those. NPVs are x cannot equal negative 2, and x cannot equal negative 7. So at negative 7, which is right here, we're going to have a vertical asymptote. So I'm going to start by drawing that. There we go. Get the whole dotted line going on in there. But then as for the rest of the function, I honestly am just going to like kind of check out on this one. We'll just divide the coordinates we have. So again, because it's f divided by g, I'm going to do red divided by blue. Let's just find some points that might be nice on this one. Here's 0 divided by 0. That's where our point of discontinuity is going to be, but who knows where it would be along our y-axis. I guess, you know what? I'm actually eating my words here. I'm just trying to find a point on my blue function. Shoot, I guess there isn't a point on my blue function that I can even find. That's going to be pretty rough. I guess what that means is it's like we have to find like a horizontal asymptote. But a horizontal asymptote, this is already an asymptote form. I know it's been a while since you've done this. Our horizontal asymptote is just going to be y equals 0. So I can just very safely say that we're going to have a point going here and a point going here, and we'll kind of just scuff it through. It'll come down like this, and then it'll come down over here. There's going to be an open circle right there, and then it's just going to keep on going. That's all it is there. And then same on this side, it's going to swoop down this way, and then it's going to swoop over this way. That's about it, folks. That's all we really got to do on this one. For domain and range, let's wrap this up. Here we go. Domain, range, f of x. Domain on f of x is all real numbers. There you go. X is an element of all real numbers. Same with the range. Y is an element of all real numbers. G of x, that's going to be our blue one. X is an element of all real numbers. Y, however, is going to be greater than or equal to our minimum point here, which coincidentally was the same as before, negative 6.25. Last but not least here, h of x is going to be a little bit more exciting. Our domain is x is an element of all real numbers, except x cannot equal negative 2. That's our point of discontinuity, this guy right over here. And x cannot equal negative 7. That's our vertical asymptote right there. As for our range could be anything except 2 numbers. So y can be an element of the real numbers, but y cannot equal 0. That's our horizontal asymptote. And y cannot also equal whatever on earth it's going to be over here. Well, to find what it is over there, you just have to plug in negative 2 into 1 over x plus 7. So that's going to be 1 over negative 2 plus 7, so 1 over 5. So y cannot equal 1 divided by 5, which is 0.2. And that's about all there is to that one. I think we're done. Yes, we are. So here's a summary. Just as with sum/difference of functions, the product or quotient of functions affects the y values. The domain of the produced function is the overlap of the domains of the component functions, just like it was before. So look for the overlap. If there was one that was restricted, you have to take account of that. And then the range of the produced function is more challenging to determine, but a graph helps immensely. So just watch that very carefully. Another thing I didn't put in the summary is when you have a quotient of function, your domain and range are both going to be limited by your NPVs. So watch for those NPVs here, okay? All right, hopefully that's it. It is, there it is. So practice, page 496, questions 2 to 8, 12, and 14. I apologize for once again a very long lesson, but hey, if you skip that last one, you probably shaved off several minutes. Not the end of the world. Anyway, best of luck, guys. If you need any help, you know how to reach me.